All right, this is a great pleasure for me to introduce Pawel Pralat from Ryerson University, who is a great expert in random graphs and combinatorics. And today Pawel will speak about, as far as I understand, relatively new process, which is called semi-random process. Pawel, please.
All right, thank you so much. Yeah, thank you so much for inviting me. It's a pleasure to give a talk to this audience. So hopefully, next time we'll be in person, but now remotely equally nice. So indeed, I'll be talking about semi-random process, and it's a joint work with various people. So maybe when the time comes, I'll mention the respective groups. So of course, I need to tell you how the process goes, and then look at three different aspects, finding perfect matchings, finding Hamilton cycles, and creating small subgraphs. So the process works as follows. So you start from with a board on n vertices. And you can think about this as a kind of a single player game. So you can just play with yourself or with the process, with randomness, and try to win this game. So initially the graph is empty. You have n vertices, and in each round, one vertex is presented to you, which is selected uniformly at random from all the vertices that are available to you. So a given vertex is selected with probability 1 over n. So on my cartoons, I will be using squares to distinguish those vertices that are selected by the process randomly. So that's my vertex U that is given to me at random, and now I can connect this vertex to anything I want. So I select vertex V and create an edge between U and V. So again, to distinguish my choices from what was offered to me by the semi-random process, I'll be using circles for my choices and squares for the choices of the process. So then what is the aim of the game? Well, the aim of the game is to create some kind of to get some monotone graph property. So monotonicity is kind of useful maybe, but it's not really needed, but it is useful to have because once you hit this property, you might want to keep it later on. But again, the objective would be to guide the process in such a way that you get your desired property as quickly as possible. So think about maybe perfect matchings for this for the time being. So your goal maybe is to create a perfect matching, and the number of vertices, let's say, is even. But any monotone graph property can be used instead, and you will see more of those properties discussed later on. But for now, we can think about perfect matching. So the game continues. Again, each round looks exactly the same as the first round. First, a random vertex is selected by the process, independently from everything else that happened so far. So a vertex U is selected with probability 1 over n. And now it's my choice. I see everything happen so far. I see the vertex that is offered to me, and I connect this to a vertex that I like. So far I have those two edges, and then oops, the random process selected a vertex that is already saturated by the matching. So that's, I'm not so happy with that, but there's not much I can do. So at that point, what do? I guess I'll just play some circle nearby, with the hope perhaps that this in some sense alternating path, because now I have an edge of a matching, let's say an edge of the non-matching. So this alternating path could be potentially useful in the future to extend the matching. So I guess that probably was a good move, but I'm not claiming it's it's a perfect strategy or anything like that. But it looks like a reasonable choice. And now some random process selected that vertex, and then I guess it makes sense to connect to one of the isolated nodes. So that's what I do. And then eventually a square lens on the next vertex. And I'm super happy with that choice, because I can finish the job by doing this and achieve a perfect matching. So one thing that maybe is worth mentioning, but it's a simple process, but just let's do it slowly so that nobody's confused and everyone is on the same page. Of course, the squares are kind of randomly showing up. So it might happen that some of the vertices will have no square, and some of the vertices will have more than one square, right? And we can, of course, make a computations. What is the probability that I have at least one vertex with 17 squares at some point of the game. So I can definitely count on some typical properties of such a random process. So let me pause for a second. I don't know if you have any questions about the process, let me know. But hopefully it makes sense, right? So, but it's a good time to clarify, because if we don't understand exactly how the process goes, then it will be difficult to follow the rest.
Yes, Pavel, just a short question. So the definition is clear, but what are the reasons to consider such processes? Maybe to somehow efficiently construct graphs that have some properties, or what was the
so I don't know what was the initial motivation of the people that introduced it, but I think it's a very natural process, and it combines as we see randomness together with some kind of deterministic decisions. So I think it's interesting in the sense that we can achieve those monotone graph properties much faster than what normally a random process would do. So I think it's kind of giving us a little bit of power to control the process, but of course some of the aspects are still random. But maybe surprisingly, maybe not so surprisingly, this additional power that we have, deterministic power, appears to be super strong. So I think there are some processes where, for example, people wanted to have a power of two choices, right? So maybe I have two edges appearing at the same time, and I want to pick one of them that is more beneficial to me. So we've seen that those kind of advantages can help us a lot, but this shows that this process is giving us even more power than those Hiloptas processes that people also consider. Yeah, so I don't think I have a good answer. So if you don't like the process, then there's not much I can do. So far, it wasn't used for anything spectacular so far, but I think it's a very natural, and hopefully I'll convince you at the end of the talk that it's also interesting, kind of from technical point of view. I think that was the main reason to introduce it. So it was introduced, or suggested by Pelek Mihaly, and then formally introduced by this group of people. I think I've heard it from Milos at one of the conferences quite recently. So I found it personally appealing and interesting. So I wanted to do more work on that, and I still work on it. So I find it nicely. I find it nice and interesting. I already mentioned that. I guess that in some sense it's a straightening of the classical random graph process, because of course, if the player plays randomly, then almost equivalently, we can think about it as a process in which edges appear randomly, and I can definitely mimic that edge random graph process if I want to, right? So I'll show examples like that in a second, but the idea again is that I will be able to mimic some of the well-known processes, including, of course, the classical and the random graph process. And of course, if I know that one of those processes create what I want to create, then of course, at least I can do that fast with my semi-random process. I could potentially do something smarter than that, but at least I have a benchmark how quickly I can achieve what I want to achieve by mimicking some well-known processes. But that's coming. But I guess this first kind of coupling we can see right now, right from the start, when we can just play randomly and mimic the arbitrary random graph process. So all the results, I guess you probably got used to that in a random graph theory. All the results I'm going to mention are asymptotic in nature, so I'll be assuming that n, the number of vertices, tends to infinity, and the results I'm going to present will hold asymptotically almost surely, meaning that the probability I get what I want to get tends to 1 as n goes to infinity. So that's the usual setup for these things. So everything I say is asymptotic, and everything I say, or almost all things that I say, will be holding asymptotic almost surely. Okay, so let's look at perfect matchings. So first observation that was already made in the original paper was another emulation. So not only you can emulate arbitrary random graph process, but you can emulate the well-known Kout process. So what's Kout process? Kout process is the process in which every vertex independently connects and randomly connects to k vertices. So there could be, of course, a few different versions of that process. One of them could be like a multigraph, where you just select k vertices one by one and don't worry about potential multiple edges. There are some versions where you can just pick k vertices uniformly at random from all the sets of size k. They're different than you, so doesn't really matter in some sense, and you are not going to escape from multigraph anyway, because again, every vertex selects k randomly selected vertices. So of course it might happen that one of my neighbors decides to select me as its neighbor. So it's in general a multigraph, and the result I'm going to mention will hold for any of the variants. So the idea here is that this is this nice semi-random process. So this is this Kout process, which is a different one, but we can mimic this process quite easily. And formally, I guess what we want to do, we want to do some kind of coupling that will create the following situation, that at time t, which of course has to be larger than k times n, but at time t, I'm hoping that my graph that is created by the semi-random process is actually a supergraph of the Kout process, right? So I want to achieve something like that. If I'm lucky, I can do it in the minimum number of rounds, but usually there's some little overhead, as you will see, hopefully in a second. But again, the idea is that I want to guide my semi-random process in such a way that this process creates a Kout graph at some point with possibly some additional edges, which I don't care about because again, I'm hoping that my semi-random process achieves some monotone property. So if I can do it, then I can reuse some known results for Kout process because if I know my property is in a Kout process, then I know it must be in a semi-random one too, right? If I can establish such a coupling. So yeah, stop me anytime you have questions. We have time. Yeah. So how do we do this coupling? Well, the situation is quite easy. Of course, you don't want kind of to wait for every vertex to be hit by, say, k squares if you want to mimic Kout. Because of course that would happen after a long time, right? By coupon collector problem, we need n log n rounds to actually hit every vertex at least one time. So if I want to hit every vertex at least 3 times, I will have to wait n log n rounds to do that. And of course, when I hit every vertex that many rounds, then I can just go randomly and mimic the Kout process. But that's of course not optimal. What I should be doing is the opposite. The first square that is given to me at random, I simply connect to the first vertex, the vertex with label 1. Then the second square, why don't we just go to the first vertex again? The third one goes to the first again, and so on. So in the first k rounds, I'm putting squares on the first vertex. Then in the following k rounds, I put a circle on the vertex number 2, and so on. So of course, since squares are showing up at random, that's exactly Kout process, right? So hopefully I convince you. Of course, you know, if we like the version where we want to go to k squares that are not overlapping for each vertex, then of course there could be some collisions. But if there is a collision, I just pause and I say, okay, I was collision, bad move. I'll just wait for the next square and connect to the right place. So that's why maybe you cannot do it in kn rounds, which would be optimal. But any function that tends to infinity added on top of it will certainly asymptotically more surely create what we want. Right, so that makes sense. So that's how we can mimic the Kout process. And why do we do that? Well, because, for example, it's known, Alan Fries proved, relatively long time ago, that the Kout process has a perfect matching if you send 2 edges at random from each vertex. If you send only 1, it's not enough, but I guess we don't need that for our purpose, but it's optimal value of k. So if we mimic 2 out process, which we may in 2n plus omega rounds, we are done. Definitely, we have a perfect matching. So this is a very simple implication using this result of Alan.
Just a short question. Sorry for interrupting you. Yeah, about the previous slide, does it hold only for constant k or for wider class of k?
Well, we don't need Okay,
I
so
see that for this it is not important.
we don't need that here, but I guess the same thing will happen with a larger value of k. Of course, you might have more collisions, so at some point you will have to start worrying about the error term here, because if you have lots of neighbors, there will be a higher chance of a collision. And if you, for example, would like to have all of those neighbors to be different, then you have to, start paying attention to that. But for moderately, for a relatively slowly growing function of k, you will have the same conclusion. But then the next question is, are there any interesting results for any other interesting results for large value of k in terms of k out process? Then I'm also not sure that there are any. So that might be useless anyway, this connection. And I think then the third comment is that if k is really large, then in some sense it's not that interesting anymore, because there's no big difference between k out process and, say, R-Renyi random graph process, right? Because again, if I have 3n edges put randomly in my graph, then R-Renyi random graph process is highly wild, because there will be lots of vertices that are isolated. This one will not have any isolated vertices, so it's nicer. And a semi-random process can even do better things because it's more powerful. So what I'm saying, I think you see a huge difference between all of these processes. But if you want to weight, say, you want to sprinkle n to the power of 3/2, say, edges in your random graph, then of course, regardless whether it's a Renyi random graph process or Kout process or whatnot, every vertex receives more or less the same number of squares. So I think the process becomes very nice and predictable. So I think, long story short, I think the most interesting questions about the semi-random process as well as Kout process are when k is a constant. So because then you have an extra power. But if k is large, and say semi-random process or Kout, doesn't matter, are almost the same, right? Because we know where the squares are going to show up, and we can count on it asymptotically or more surely. So I think the process behaves much more predictable. Because I think the main hope is that our algorithms can be adaptive, in the sense that I can watch which vertex becomes unlucky, in the sense that no squares land on that vertex, and react accordingly. So that's the biggest advantage. Yeah, but already we see that a huge power of the semi-random process, or through the Kout process, because if you want to wait for perfect matching in a random graph, in a Renyi random graph process, then you would have to kill, of course, all the isolated nodes, which happens after roughly half n log n steps. So it will be much longer. Here because of the adaptive strategy, we can do it much faster already with just mimicking Kout process. Another improvement that we can put on top of it is we can actually emulate something a little bit sparser, namely the so-called 1+2/E_out process. And that's a bipartite graph. So it's slightly more complicated, but not too much. So hopefully it will be clear from the cartoon what we're doing. So we start with the so-called, we start with the Oneout bipartite process. So what do we do? If when the maybe what's Oneout process first? Oneout process is that every vertex on top is selecting one randomly selected vertex at the bottom. So every vertex on top will have a random neighbor at the bottom, and every vertex at the bottom is doing the same, selecting one random vertex on top. So that's a one-out bipartite process. First question maybe we should ask ourselves, can we mimic this by semi-random process? And the answer is yes. I hope you agree, because what can we do? Well, if the square lands at the bottom, so I condition on the square landing at the bottom. If the square lands at the bottom, it's a random place at the bottom, of course, and then I can simply connect to the first vertex on top. If the square lands on the top, maybe when I don't reveal the information where it is, but all I know is at the top, I connect to the first unsaturated vertex at the bottom. So if the square lands here, I just go one by one, keep putting square circles on top, and then if something lands at the top, I'm selecting squares one by one from the bottom. So of course, after exactly n rounds, well, there will be slightly more squares and then one of the sides than the other, right? So, one of the sides will probably have half n plus root of n squares, and the bottom part will have less that. But of course, what I can do is I can run this for n plus some root of n, say omega rounds, and this way it will be guaranteed asymptotically almost surely that that the bottom part receives at least half n squares and the top part receives at least half n squares. So maybe not in n rounds, but in n plus little of n rounds, I can definitely mimic bipartite version of the one-out process. All right, so that's part of the game. Now, what this 1 plus 2 out 2e out process does, well, the process stops at that point. And what is the situation? So it's only half of my picture for a better, for an easier read. What is the situation? Every vertex on the top selected one random square at the bottom. So I have 1 over e fraction of the vertices at the bottom that don't have any square. So that you can make a computations, but that's easy to do. That's how much you expect, and that's how much you have asymptotically almost surely. You can use some standard techniques like second moment method to show that. And the same here. The number of squares the number of vertices at the bottom which received only 1 square is 1 over e fraction of that, and so on. So in some sense, the fractions are following the Poisson degree distribution, Poisson distribution. So we can have precisely, we know precisely how many lucky guys you have at the bottom and the top. But the most important thing is that 1 over e fraction has nobody, and 1 of e fraction has precisely 1 square. And that's our unpopular vertices. So we call those vertices unpopular, and these guys can choose another neighbor, so they get extra power for free. So that's the process, and it's known that this process has a perfect matching, and of course it's a little bit sparser than 2-out process, because how many edges we have? Well, not 2, not 2n, but 1 plus 2 over e, which is less than 2 edges. So in fact, this is a little story, but if you start Googling, don't be surprised. In fact, in the initial paper was showing that we don't need to give extra power to those vertices. Only it's enough to give those with 0 squares So there is a paper, older version of that one available and published in JCTB, which announced that 1 plus 1 over E out process has the matching. But when I wanted to improve the result, of course, I've read this paper, and there were some problems which I couldn't fix. But Boris Pittel looked at that, and he found out that it was actually wrong. So 1 plus 2, 1 over E process does not have a perfect matching, but 2 over E is enough. So unfortunately, the weaker bound can be established, but now we have a better understanding of this process. But anyway, so that's the upper bound we have so far. The question is, can we do better than that? So there is hope, because the Kout process, in some sense, it's not really adaptive process, right? So we know from the very start what do we plan to do. This one is a little bit better, right? Because I do Oneout process, and then I stop and pause for a second, look who is unpopular, and do something smart to make it work. So it's adaptive in the sense that I have one point of the process. I have time to recalibrate my strategy and do something better. But only one thing, right? There's only one time after doing Oneout, I identify who is unpopular, and do something that makes sense. So that's already much better, but it's only one time. So if you keep watching the game and do something smart in every single step of the process, you should be able to get something better. So together with Jane Gao and Callum McGrory, we had a look at that, and we proved the following upper bound, which I hope you see it's better, not worse used to be. This constant is actually a solution to some differential equation, and you will see why differential equations show up on the screen in a second. Let me mention a few words about this algorithm. So this algorithm is fully adaptive. So that's the advantage of that. Maybe just to warm up, I can give you something slightly weaker, but probably easier to understand. And then maybe mention how we can actually squeeze this 1.2 out of this algorithm. So what do? We have, I don't know if I have a cartoon. Yes, I do. So we keep constructing matching gridly. So at some point I have a matching like this. But then what do I want to keep track of on top of it? I want to keep track of potential alternating paths. So when the square lands at the bottom, then of course I'm super happy and lucky. I'm just extending my matching to the next vertex and just say move this edge up. So if something lands on the unsaturated vertex, I know what to do. But if something lands on a vertex on the matching, what do I do? For this toy warm-up algorithm, I'm simply jumping randomly to one of the nodes, one of the vertices to the bottom. Right. So if the square lands on the saturated vertex, I go randomly to one of those guys that are not saturated. So why do I do that? Well, I've probably seen this already in my semi-random process cartoon I had at the very beginning, because this creates a nice spot, extra spot here. We call it red vertex, because if the square lands on the red vertex, I can create a augmenting path. So by going down, I can replace the edge of the matching that I have with two edges and increase my matching. So I can absorb these two vertices. So yeah, I think that's exactly what happens. So for an easier analysis of this warm-up algorithm, we can simply track only one extension, right? So of course the question is, what do we do if the second square lands here? Of course, you know, it makes probably sense to not to pause and not to just give up and say, okay, I don't care about that second square. You still might want to go randomly to the unsaturated nodes. And why do we do that? Because when I make an augmentation, and let's say replace that edge of the matching with those two edges of the matching, if I have some extra squares going to outside randomly, then even after augmentation, I have some vertices with at least one square that are ready to be augmented as well, right? So one more time, if I in this warm-up algorithm, if I only keep track of one random extension, then that's of course much easier to analyze. But the disadvantage is that, you know, when I do an augmentation, my red spot, which I really liked, disappears. There are no red spots anymore. But if I keep track of how many saturated vertices have, say, two squares, then after such augmentation, I still have red nodes, right? Because this wouldn't be red, but I guess this would be a red edge of the perfect matching. But this guy will have still a one random edge sticking to downstairs, so I'll still keep red nodes in my matching. So this can be improved, and that's how we improve it, of course. And the other improvement is that for simpler analysis, we can have random edges. So I might select my verse at the bottom randomly, but it makes more sense to actually do it in a greedy fashion. So every vertex downstairs, it's better if every vertex downstairs has L or L+1 neighbors upstairs. And then when I make a decision, where should I extend my new square to, I go to greedily to a vertex with less circles on them. So that's, yeah, I think I probably told you everything I have on this new slide about, you know, the possible extension. But maybe before I summarize it again, why do we see this differential equation? Well, because as you may guess, those random variables that track how many nodes, how many vertices of certain type I have, how many red spots I have, and so on. This is a random variable, and I can track how you know, how they change, what is the expected change. And there is a nice method developed by Nick Wormold, which allows us to analyze these kind of random variables. So if you haven't seen that, you know, I strongly encourage you to look at this. This is a fantastic tool and super exciting. But the idea is that, again, maybe just in a one sentence or two, you do like, you look at all your random variables, you compute the expected change, then you put your physics hat on, you know, replace your math hat with your physics hat and say, okay, let me just pretend for a second that all those expected changes are actually happening, and you get a difference equations, and then you do another cheat and you say, okay, let's just assume that since n is tending to infinity, those difference equations are really differential equations, and you solve it, and then the magic happens. You use the differential equation method, which tells you that your random variables, asymptotically or surely, are very close to the solution of this differential equation. So there have to be some additional properties that need to be checked, such as you know, your system of differential equation, system of random variables has to be Lipschitz. You don't want to have too drastic changes in the random variables in one round, because at the end of the day, under the hood, of course, you apply tools such as, you know, having a zoom inequality, where you need to track not only the expected changes, but you also need to track the maximum changes. So anyway, I'm not showing you any details. I'm not even showing you any differential equations. But if you haven't seen that method, I suggest to look at this. It's great, and there are some ready-to-use black box theorems by Nick, and now Lutz Warnke is also looking at these kind of tools, and many other people. So they're strong and nice tools. Yeah, so then this warm up algorithm was only one extension and random to make it simple, but to squeeze 1.2 instead of 128, you need to do greedy choices for your circles, as I mentioned earlier. And actually, we went all the way to 1100 phases. So you have to glue your phases. So there's some job that needs to be done by your favorite software. And then once you do those greedy phases, we come back to the random phase, because it's still some verses are not saturated. We cannot go all the way to the end because, as you can guess, the number of unsaturated verses, of course, is shrinking. So at some point, there's some singularities in the differential equation. So you have to stop at some point where you have some really small number of unsaturated verses, but still linear. And then you need to theoretically analyze that you can kill the rest. So this is what needs to be done to make this argument rigorous. But it's not that complicated and lots of fun. So there are different components. So to get the Beres constant, you have to do greedy phases, then kill the rest with just a random phase, because you don't want to consider too many phases. And then once they're like 10 to the minus 16 times n verses to saturate, then you just do the theoretical saturation, because essentially root of that constant, so I don't remember if you have 10 to the minus 8 or whatever it was, so say 10 to the minus 8 can be killed definitely in 10 to the minus 4 times n rounds, and that's negligible. So that's what needs to be done.
Pavel, just a short question. Does this beta come only from this random phase?
No, I think it's all together. So it's yeah. So this is the main ingredient, right? So I don't remember exactly, but I think after those 1100 deterministic phases, there were like say 10 to the minus 3 verses not saturated yet. So very tiny, but still not enough for the cleanup, because that would destroy our numerics. So we had to do this just to get to something ridiculously small, like 10 to the minus 8, so that the root of 10 to the minus 8 is negligible. So, you know, those phases is the main ingredient, and that's what this beta is essentially coming from. And plus this random phase, and that's beta. But most of it is this, and the cleanup, that will be this tiny error term. Yeah, so this warm-up exercise is easier because there's only one random phase, right? So this is just one random phase plus the cleanup. So just one differential equation, very simple one to solve, and you're done. But yeah, this one was to just squeeze a little bit more numerically from the argument. But definitely, yeah, if you don't care about the constant much, then the warm-up algorithm is much easier to analyze, and you can do it on a piece of paper, perhaps even. You don't need any maple to do the job for you, but of course with 11,000 deterministic phases, you don't want to do it by hand, but it's easy for maple. Okay, so what about the lower bound? So here, trivially, of course, yeah, this is a maybe trivial, insulting observation, but you know, of course, we cannot do perfect matching in less than n/2 rounds. But you can improve it a little bit by the following with the following observation, and maybe surprisingly, both trivial necessary conditions actually give us the same lower bound. So what are those? Well, if I dream to have a perfect matching, then I better have a vertex. All the vertices should have a degree at least 1. So that's one trivial necessary condition. And then the other necessary condition is that, look, when I have a semi-random process, every edge has a square connected to a circle, right? So if I have n/2 edges in a perfect matching, then I better have at least n/2 vertices with at least 1 square, because otherwise, you know, I cannot do my perfect matching. So we have those two trivial conditions, and both of them give us exactly the same lower bound, namely, so there are two different arguments, but the same bound, namely log base e, so natural logarithm of 2, which is of course slightly better than half n. So this is the lower bound. So maybe one sentence about, you know, these how to get there. So I guess this observation is easy, right? You don't need anything fancy, because again, by coupon collector problem, you can compute and use second moment method to compute, you know, how many vertices without a square do I have, and you get that after Cn rounds, you essentially get e to the minus c fraction of those guys not saturated. So if you want e to the minus c to be half, you better take ln 2 as your c. So that shows why we need that. I guess this one is harder, perhaps, right? I don't know, unless I'm missing something. This one is slightly harder because, you know, if I tell you create a graph with, or in other words, kill all the isolated vertices in your graph, then of course you know what to do. You need to jump, and each time you destroy one isolated vertex. But of course, sometimes you destroy a isolated vertex, and then the square lands on that vertex. So, but anyway, you can show simple coupling that's the best strategy you can do. If you want to kill all the isolates, you should just put your square on isolates, and then you can use the differential equation method to analyze this process, and you get exactly the same bound. Log base 2 n is how long does it take to kill all isolated nodes. So both bounds got the same lower bounds. Both arguments give the same lower bound. So yeah, that was observed by these guys, and we also improved that lower bound from whatever 69 to 93. So another, I guess, constant, but this time is computed more explicitly. It's also numerically, but it's just the infimum over b, where this ugly-looking function is at least half. So I guess we should be able to hopefully see why this function appears. But before that, there's a little annoying issue. For the differential equation method, or for the Hebninger-Zuman inequality to work, again, we would need to have the property that in one step we won't change our random variables by match. But the problem is that nobody can stop the player from placing circles on one vertex. So a player can put can create a star if the player really wants to, right? So how do we deal with that? So on one hand, it's very silly, right? If I want to create a perfect matching, I'm a player. I shouldn't be placing trillion circles on one square. On one vertex. That's clearly a suboptimal strategy. Only one of those edges will be useful for my matching, but nobody can stop the player from doing that. But on the other hand, to show the lower bound, you have to show that no matter what the player is doing, the player will not be able to achieve the perfect matching, right? So how do we do that? This clear silly strategy is destroying our argument. So this is a little bit annoying, and it's surprising that it took us like 3 pages in the proof to actually deal with this annoying issue. But the way we solve this is to offer the player a deal. So the deal is pretty straightforward, but the proof, that's a good deal is maybe, well, it requires a few lines. But we ask the player the following: well, why don't you play the following game instead of playing perfect matching game? Namely, please don't put more than 2 omega circles on one vertex. So we restrict you from doing that. We ask you kindly don't do that. And as an incentive, we say if you don't do that, then the game will be done. We'll finish the game when you create a matching which is saturating almost all vertices. We don't want you to create a perfect matching. We'll be happy if you create an almost perfect matching. If you create n/2 minus some little of n over omega edges. So I hope you see, right, that it's a good deal. Namely, if the player, say, creates in the original game a vertex with 2 omega circles on them, then of course it's a waste of lots of energy, right? But I only can gain 1 edge in the matching because of that silly move. So it's more beneficial for you to just say, okay, so I just don't do that, and I get, in some sense, this vertex for free. Again, simple coupling can show that if I can win the original game, then I can certainly win this auxiliary game. So for me, there's no point, if I'm offered the deal, there's no point for me to play the original game. I'll simply be playing this auxiliary game. And now the good thing is that this auxiliary game is easier to analyze, because again, if I don't have any vertices with more than root of n circles on them, then the maximum change in my random variables is going to be at most root of n, and that's enough for the differential equation method, or for having a zoom inequality to kick in and work for me. So this is kind of like, yeah, a little annoying issue that we need to deal with. Now we control a few things. One thing is we control the number of vertices with at least one square on them. And I mentioned that's you don't need anything fancy here. Just a second moment method is enough to show that this random variable asymptotically or surely is going to be well concentrated around what we expect it should. So those vertices with at least one square, they keep increasing in size, and we know what's going on with them. But now on top of it, and if I just use that, right, one more time, if I use just that, then I recover this trivial lower bound we had earlier, namely we get this log of 2 as a bound, right? Because again, we need this xt to be at least half n. So I want my t to be log 2 times n, right? So that 1 minus half is half, and I'm happy. So if you, yeah, so that's exactly the trivial bound. But now what we want to put on top of it, we want to take into account that the semi-random process is giving me squares randomly. So some of the squares by pure randomness are going to be useless. So what do I mean by that? Well, let's imagine the following situation. At some point, square lands here. Well, I have to do something. So I extend this square to a circle. So at time s, I got a square. I put my circle here, and that vertex we should pay attention to. And then what happens after? Well, after times s, nobody else landed on this vertex. So this vertex has only one square on him, and then this circle received at least one square after. So maybe after one square was extended, maybe another square extended. So I'm really happy with that situation. I guess, well, happy because I try to improve the lower bound. I guess if you're playing that game, then you're not so happy, because this square is in some sense a little bit useless, right? Because it's redundant. Because if I use this square for my matching, then I wouldn't be able to use those squares for my matching. And vice versa, if I use one of them for my matching, I wouldn't be able to use this one for my matching. So unfortunately, this square, well, both vertices are counted in this random variable. Both of them have at least one square on them, but I cannot use both of them, right? Only one of them can be used, so the other one is redundant. So if I keep track, how many of those redundant verses I have, I can do a better, I can do better lower bound. So that's what we keep track of, this UT. There's one more technicality, I guess, because those useless are actually not total useless, because if you can imagine that you have a redundant guy connected to redundant, connected to redundant, connected to redundant, so a long path like that, then of course I cannot use all of them for my matching, but I can use half of them for my matching, right? Every second one can be used, every second one is useless. So they're kind of half useless, or they could potentially be half useful and half useless. So on top of it, I need to keep track of those chains of redundant nodes. But before that, one thing that I don't think I mentioned, it's good that I put a comment on this. The important thing is that this random variable UT actually does not depend on the strategy of the player, right? And that's why we wanted those squares to be kind of after the circle was placed. Of course, if the player is putting circle on the square already, it makes it kind of tricky for the player, but that will be hard to track. And I want to have something that is only affected by the process, not necessarily by the player. So this is what we do. So it's a weaker bound, but something that is analyzable. So that's important, that this random variable UT is just a function of the process. Not the player has no chance to affect this random variable. Okay, so that's it. And then I mentioned I need to keep track of those chains. So we have the so-called well-positioned guys, which is simply saying I have a redundant vertex which has one circle, precisely one circle connected because it's just one square. And then this one is also redundant because something arrived here after times s, and that was the only square on that node. So we can have some chains of redundant nodes, and that will be called well-positioned. And we can keep track of those. And then the observation that is relatively easy is that those verses that I have with at least one square, those are important. But then if I have some redundant ones, I lose my power. If I have some one position ones, I regain my power from those. But this thing has to be at least half n in order to be able to create a matching. But we actually need to have a little bit less than half n, but no, numerically it is of course negligible because of this deal that we offer to the player. We're not really aiming for a perfect matching, we're aiming for near perfect matching, but numerically again, it's the same because this term is going to be negligible, of smaller order than half n. And again, differential equation method kicks in, and the function g that we've seen earlier, I don't know, a long time ago now. Yeah, this one is just a sum of all those solutions to the differential equation. So we want that tracks the sum that I had on the left, and I want this to be at least half. So that gives me the condition, which turns out to be much better lower bound. But not surprisingly, right? Because again, we have quite a bit of those redundant squares. So I need to play a little bit longer to have much more vertices with at least one square than half of the number of vertices, because those redundant ones are useless or half useless to me. Okay, so that's perfect matchings, and I know I talk slowly because I think this presentation normally I would probably tell in 50 to 60 minutes, but I think I have more, so I'm talking slowly. But don't worry, because I don't want to talk about Hamiltonian cycles a lot, so I should be done relatively soon, because yeah, you will see in a second. It's still in some sense work in progress, but let's start from the beginning. Again, since we know we can couple a semi-random process with Kout process, we can use the nice result of Alan Fries again and Tom Booman that says that 3-out process is Hamiltonian. It's actually a long series of papers. I don't have a whole history of that, but it was proved first for huge value of k, and then going down all the way to 3. So there was like a long process to analyze Kout process, but now we know k is equal to 3 is enough, and k equals to 2 is not enough. So immediately we get that 3 n roughly rounds is enough to create a Hamiltonian cycle. And the question is, can we do it better? And we did, and that's with a different well, not different, I guess, still Jane and Callum. But we also asked my friend Bogumił Kamiński, who is an expert in numerical methods, operation research and whatnot, because in order to get our upper bound, we had very sophisticated high-dimensional optimization problem to solve, and he was, we were hoping that he can help us to solve it. But unfortunately, in some sense, we only managed to have a strong evidence that the bound that we claim is that. So I guess really in this, for this crowd, I think it's probably not even a proof, but I guess we by doing extensive simulations, I guess we proved that the probability that this bound doesn't hold is 10 to the minus trillion, whatever. So so the bound is with high probability in a different sense true, but it's some kind of weird optimization problem that we cannot solve. You just have a strong evidence that it's much smaller than 3. But anyway, it's in some sense nice paper maybe, but I don't encourage you to read it maybe, because it's kind of fairly long. Uses some nice ideas like Poisson rotation, standard tricks, but some nice ideas to get this result. But if it's a shame that it's not really a theorem in our sense, and then maybe good thing is that it was actually accepted quickly and published quickly, because quite recently we realized that by doing some I guess after our experience with perfect matchings, we realized that we can do a fully adaptive algorithm for Hamilton cycles. So that's a work in progress right now. It's not done yet, but we're kind of shocked because this is a fairly sophisticated algorithm, which is only supported numerically, but we have now nice ideas for fully adaptive algorithm that short argument gives us something like 2.06. So I guess we had now an option to publish like a 3-page long paper on this, or try to do something more sophisticated and hopefully go below 2. So this is what we are doing now, slightly more complicated argument, and we keep fingers crossed that it will, for some reason, we cross 2, because I think that would justify maybe why we do it. But anyway, so that's I think all I want to say about the Hamilton cycles, because we have some results, nice ideas, but at the end of the day, relatively weak bound and only numerical. So wait for maybe for the fully adaptive algorithm, which should be much easier paper to read and much stronger bound and to get. And the same with lower bound. It's another maybe a little shame. The lower bound, by analyzing the greedy algorithm. So if I tell the player, you know what, forget about Hamilton cycles. Why don't you just try to have a minimum degree 2 graph? Then it's easy to see what the best strategy is, and it's easy to see, again, using the function equation methods, to compute how long it's going to take to do it. So first of all, you kill isolated vertices, and that will take you log n times n steps roughly. And then once you kill all isolated nodes, you kill all the nodes greedily with degree 1, and that will take you another log 1 plus log 2 rounds, and in total, that's how much you need. So this is the the lower bound using this min degree 2 argument. And again, we had a look at that and try to show that you cannot do Hamilton cycles in that step. And surprisingly, like the perfect matchings were good, right? Like we managed to improve the lower bound by quite a bit. Here, it's kind of silly improvement. So numerically, even it's not visible. I cannot, we cannot change 3 to 4. But just to show that the lower bound, the current lower bound, is certainly not the right one, which I guess most of the people believe anyway. We proved that there is a separation from the current lower bound by epsilon, but unfortunately, this epsilon is really ridiculously small. So that's just a short argument in the paper, but nothing really to be proud of, I guess. But on the other hand, maybe interesting in a sense that we know, which we suspected, that the lower bound is not the right one. So still, the gap is quite substantial. I don't know how far below. I hope we go below 2, but I don't know how much. Probably not much below 2. So the upper bound will be close to 2, and the lower bound is still very close to 121. So this problem is wide open for Hamilton cycles. And then let me spend the last 5 minutes I have left, or 10, talking about small subgraphs. So the game here is to create a fixed graph G. So again, all the results are asymptotic, but now the graph is fixed. Let's say your favorite graph on 15 nodes, or Peterson graph, whatever you want. Pick your favorite graph G. And now, if this graph has degeneracy D, then we know we can quickly create it in roughly n to the d minus 1 over d rounds. So very quickly, right? Because it's sublinear number of rounds. And how do we do it? Well, the situation is relatively easy. So this is my 2-degenerate graph. Let's say you create. And do I have cartoon? Yeah, I do. So let's say you want to create this graph. And let's say at some point you have already half of it. So you have a graph induced on V1, V2, V3. So you have this little triangle. So you have a triangle already created. And now let's try to create one more, let's try to add one more vertex on top of it. So what can I do? Every time a square lands somewhere, I connect. Where should I connect V4? Well, V4 should be connected to V2, and then should be also connected to V3 in kind of my degeneracy sequence. So I'm waiting for my squares. Every time the square lands on the brand new vertex, I connect it to V2. But when one of those vertices receive another square, I connect it to V3, and that's of course my extension that I need, and that will take less than that many rounds. So that's how long they have to wait. And if the graph is finite, the graph only has 6 nodes, then of course you can just do it 6 times and you're done. So this is a very nice, simple strategy to create a degenerate graph. And in this strategy, the analysis is the best possible, because if I, instead of dividing by omega, is multiplying by omega, I divide by omega, then unfortunately I won't see any vertices with d squares, so I won't be able to achieve what I want to achieve. But of course, it doesn't mean that there's no other strategy. They, in the original paper, proved that there's no better strategy if you deal with complete graphs. So they conjectured in that paper that if I have a degeneracy D graph, I can deal with this times omega, but I cannot do it in less than this divided by omega rounds. And they proved the conjecture for the clicks, but that's it. It was wide open for the remaining ones. So with a different group of people, with my postdocs, Natalie and Trent, and also Andrzej Rucinski, I think, yeah, that was still, I think we met at some point in Barbados, I think, and I mentioned this problem to him and he liked it. So we did this together. We proved that the conjecture is true. And I'm not going to show you the argument. It's a bit technical, but yeah, the paper is available on arXiv, so that we know the conjecture is true. And then we realized that everything we proved actually translates immediately to the hypergraph setting, where, let's say, you want to create a uniform hypergraph, and one square appears and two circles you can add on top of it. So everything can be immediately translated to the hypergraphs, for which you have still one square and arbitrary number of circles. However, and maybe that's surprising, when you have more squares and only, say, one circle, vice versa, then our result does not translate. And as an open problem, we spent some time thinking about it, but not a lot. So I don't know, hopefully it's not too easy. But for example, question like two squares are presented. You are responsible for one circle. So we are dealing with three uniform hypergraphs. And let's say you want to create a click. So even clicks are open of size 6. This is the smallest graph I'm aware of for which we don't know what the answer is. We have some upper bound, some lower bound, but they don't match. So I think if you like this problem, I like hypergraphs, then I think that's the nice warm-up exercise, or maybe it's not warm-up, it's difficult, I don't know. But one open question that is annoying because it is a very small graph, it's a click. So I would guess that maybe solving, because again this conjecture is true, and the conjecture is true for hypergraphs with one square for all graphs. So I was hoping that with two circles and one square, at least we can do clicks and maybe leave it open for other graphs, but other hypergraphs. But yeah, case 6 is still open, and that's kind of weird and annoying. So I think I leave you with that question. Let me know if you solve it. But yeah, I'll probably try to do it again when I rest it. But if you're faster, then oh well, there's not much I can do. Thank you so much. Yeah, that's it I have.
Thank you very much, Pawel. Any questions? Do you have any conjectures on these constants in front of n in optimal number of steps for matchings or for Hamiltonian cycle?
Yeah, I don't think there is anything natural that comes to mind immediately, right? So I don't think there's, I've never seen any conjecture, and I would be surprised if it has some meaning. But yeah, I guess we'll know once we get there. Hopefully we'll get there. But yeah, that's a good question, but I have no intuition. And yeah, even like what should be like what for perfect matchings, we have this 93 and whatever it was, 1.2. So yeah, so that's I don't even know if whether it should be above 1 or below 1. Even that, I don't know what to conjecture. And I guess the same applies to Hamilton cycles. I think there's no natural number that I can think of. So I think I would guess, I would bet on both bounds that we have so far are not the right ones. So it's somewhere in between.
Mm-hmm. But am I right that you even don't know how to prove that that a constant exists? It is not that it is concentrated.
Yes. So I didn't do that, but yeah, if you look at the paper, you can of course do you can define it in a more rigorous way. This constant. So you simply, I guess, say what is the how many rounds do we need for every strategy so that the probability. The probability that I achieve what I want to achieve is at least Q, and then take a limit when Q tends to 1, and then you also have a limit with N. But if you set it up properly, you get what you want. So namely, you get the constant is well defined.
Mm-hmm. Yeah, I see. What about these extensions to hypergraphs? Are they published?
No, so this is in this paper with Andrzej Ruciński and postdocs. So it's on arXiv. It's not published. It's on arXiv. So
the hypergraph case is also considered in this paper.
Yeah. So we proved the conjecture for graphs, and then we realized it's that our lower bound, our proof translates immediately to hypergraphs with 1 square, and of course the same applies to upper bound, right? Of course, you have to have a different notion of the degeneracy here. So we want to have the property that every, I guess, the same property. I guess every vertex has to be involved in at most D hyper edges to the left. And then of course you can use this property to create your hypergraph, because you know where to connect, where you put your circles once your square appears. But yeah, with 2 circles, it's surprisingly we don't know what it is. So yeah, it's all in the same paper. Maybe it's a bit much. So we were thinking about splitting maybe into 2, but at the end we just put it into 1, because really the lower bound for hypergraphs is exactly the same as the lower bound for graphs. So, and then the same applies to, so one square hypergraphs is exactly the same argument, both upper bound and lower bound. So we put it all together. Yeah, but I don't think anyone has looked at hypergraphs. But I think this is a brand new process. I didn't mention the whole history. I think there's some also results. I think Nogalon asked a question about this the semi-random process, which was then answered by Michael Krivolevich and his team. If I remember, the idea was that they wanted to create a graph on n vertices. So it's not like this. It's a little bit like this small subgraph, but in our case, the graph is small, fixed in advance. But in their case, they want to create a graph that is a spanning graph with a maximum degree at most delta. And the question was, how long do you have to wait to create it? And not surprisingly, I guess, if delta is, let's say, tending to infinity faster than log n, because we know how many squares each vertex is going to receive, then maybe it's not that surprising that we can actually create this graph in a delta over 2 n rounds, right? So we can just use your squares for edges, but then also half of them will be coming from circles. So, long story short, I think, again, the same story as we had earlier. If you wait long enough, then the process becomes predictable. But what they also proved is that if delta is tending to infinity, but not too fast, then I think they proved that you need only like 2 delta times n or 3/2 delta times n, something like that, rounds to achieve the goal. So that's nice. I think that was like a Soda or Fox paper. So quite nice result. So yeah, there were some other things happening, but I think what I wanted to say, and that's why I want to mention that, I think except those few results, so I think everything you've seen today, plus maybe Michael's paper, I think that's probably everything that is known about this semi-random process. So everything is open. So that's exciting in the sense that, you can pick your favorite monotone graph property and yeah, prove your bounds there. Yeah, so I don't know who else is looking at this. I'm sure some people are looking at that, but it still looks like it could be relatively easy to get some results. And the same applies to hypergraphs. I guess nobody. We just introduced this game for hypergraphs, so this everything is open there.
Thanks. Interesting. Any other questions? All right. It seems that there are no other questions. Thank you very much, Pawel. It was really interesting and clear. Yeah, not so clear to understand all the details, but we should look to the paper.
Yeah, well, that's always the idea, to just tell the big picture. Hopefully, it wasn't. Yeah, it was clear, and then yeah. So, like I said, you should be able to finish the job with Hamilton cycles, but yeah, this is the work in progress. But I think that the process itself has a lot of interesting properties, and hypergraphs are wide open. So I'm sure I'll continue working on it.
Right. So looking forward to see sharp results of Hamiltonian cycles.
Well, not too early, unless you join the crowd and maybe you do it. No, but I think it's fun problem to look at. So.
Yeah, that's right. All right. Thank you, Pawel.
Thank you so much for the invitation again. Yeah. Have a good day.
Yeah.
Have a good evening.
Bye-bye.